My name is Ulrich Bodenhausen. Welcome to my presentation. After a short introduction to AI in the automotive domain, I will explain behavior of AI systems, and I will then present 4 principles of view that will be important for the application of AI in the automotive development. AI offers great opportunities for new or enhanced functionalities. So how can we use AI in automotive? First of all, we can use it to implement complex functions that would need many years of improvement if implemented and optimized manually. Secondly, it can be used for innovative user interfaces like speech recognition, and this is where I was working on some time ago. And this can be very well used to make driving feel more comfortable, to feel more modern, to feel more like a mobile device or whatsoever. On top of that, it can also be used for predictive maintenance. In my presentation today, I will talk about this first field of application, and if you see on the right hand side the electric powertrain architecture, you have a battery, you have an inverter, you have an electric motor, and it's a simplified architecture, but in principle you have two level controls. We have a low level control, it can apply to that, and it can be applied on the high level control, like the driving strategy or the shifting strategy or whatsoever. And if you look at BEV and HEV, they are both new, comparatively new compared to the combustion engine. And so we do not have the decades of experience. We do not have the decades of manual improvement. So the idea is, why not use artificial intelligence to help us in the optimization, make it more smoothly, make it more efficient, because if we don't do it, somebody else will do it. So how does this general scenario look like? You have a car. Inside the car you have an ECU or you have a domain controller, and the domain controller is connected to sensors. You may have an artificial module in the car on top of this ECU or the domain controller, and it may be connected over the air to a backend or to a cloud outside, and you do the AI outside. So this is an example of the main years of data analysis improvement on how the clutch is changed. So it's some old data, but there has been a constant improvement over the decades. And if you think of the driving comfort you have today by the automatic gears, it's so comfortable, it's so efficient. Yeah? It's not comparable you had 10 or 15 years ago. So why not use something that helps us to do the optimization fast and efficient in applying this to HEV and BEV drivetrains, because we do not have yet the experience. So if we look at AI software, what is it? Is it just classic software development? And of course you have to implement code, you have to put modules from a library together, and for classic software development you just compile that, and in principle you can use the result of the compilation process in your car. For AI software development, then you have this phase of training, adjustment. Internal parameters of this module are adjusted by learning algorithms based on data sets. How does it work? So if you look at the generic deep learning neural network, you have an input layer, you have an output layer, and you present a training pattern to the input. Then it is processed internally by all these connections and units, and then you get a result at the output. Then you compare the desired output with every output you have, and based on that the training algorithm does some adjustment of the internal parameters. So then you take a set of test cases to figure out how well is this and doing. The purpose is to measure the performance during the development. So now there is one concept for this learning algorithm that is called generalization ability, and let me explain it to you. As I'm a physicist, I explain things by using the simplest possible example I have, and this is a switching function. If x is greater than 0.5, the output shall be 1, and if x is smaller than 0.5, the output shall be 0. And in case of a learning pattern, we have several patterns we use as training data here to train our system. Now on the right hand side we see something that is called decision boundaries. So these learning algorithms of classifiers, they tend to learn decision boundaries between several classes. And in our very simplistic example of the switching function, it may look like this. So, and the green dots represent the training cases we have. We then have now the testing data, and you see they are different from the training data. And we see what happens is that one specific case, if x is 0.5, the thing does wrong. We see here, and it's the red circle around it, exactly for this one pattern, the thing has not learned it correctly. And if we go deeper into the analysis, we figure out that there is not enough data in the surrounding of this decision boundary to make the system able to learn correctly what the best decision boundary is. You'll get back to that later. So now we have to conclude, and in the preparation of this I looked up with speech recognition what the weather would be in Berlin, and this of course works very, very well, and this performance would not be possible without AI. So if you look at deep learning neural networks, they are very powerful, and the good news is they can learn very complex functions. All this speech recognition would not be possible without AI. And they can generalize well. And if you look at these systems, that really works well today. The bad news is that also the recent research cannot tell how well this generalization will be. We do not have a concise explanation of the generalization ability, and we do not have a practical measure for it. So what we need to do to bridge the gap, we need principles to apply to do as best as possible and to get the best out of AI. So now I have brought 4 principles to you that I would like to present to you. And the first one is to continuous improvement of the database. Second one is to use data augmentation. Third one is to keep test data independent. And the fourth one is to do software test of the AI module frequently and with the full data that is available. So let's come to the first principle. And these are pictures from lessons from the automated driving. Do you need new objects or do you need no objects? That is the question. And the left-hand picture shows a road participant. It's a cow on the street, and for a rural street this might be the right road participant, and you need to be able to detect the cow on the street. And this is called an edge case. It's not the usual case. You don't have to expect cows every day and every hour on the street, but it can happen. On the right-hand picture, you see an empty street. So, of course, it does not help to collect much more data from these empty streets. So what I want to tell you, of course, we need to improve our database for the so-called edge cases, for the cow on the street. And of course, it would be easiest to get the most data from the empty street, but both will not be the best. You have to somehow look what is in between, what is our usual business, and we need to get the conditions, the data for that perfect with a much higher importance. So how do we do it? What happens in these learning systems? And I brought you an example from a classifier distinguishing 26 classes. This is a confusion matrix. And what it means, in the diagonal you see the correct cases. Yeah? So class A is detected as class A. And outside of this diagonal you have, first of all, the false positives, and you have the false negatives. And what I want to show you with this example is that the problem cases that you have, the false negatives and the false positives, they are not uniformly distributed. In real world problems, there are very likely certain areas, certain classes that are confused more often. And my recommendation is to also optimize my database improvement to just match that fact. So to look into a developer story, analyze concerning performance requirements. So we need to look for false negatives, false positives. We need to analyze the frequency of that. And then we need to find out to guide our data collection, data preprocessing, to really look for these spots where we need to optimize our decision boundary. We remember the decision boundary from the simple switch, and you can figure out that for complex classifiers, for complex analysis with AI, this decision boundary is highly nonlinear. But however, there are methods how you can improve the data collection just to get more data or better data points where it matters most. And this is the message I have for you. And I've brought two references here, recent research that tells you there is something going on. We do not have to collect data uniformly. We can figure out where do we best gain improvement by data improvement. Second principle is data augmentation. On the right hand side you see what it is. It's obviously the same picture, but it's transformed. It's a little bit moved, it's a little bit scaled. So scaling, cropping, rotation, brightness, or combinations of these are all linear transformations that can be done to improve your database. And of course, this should be used. However, if you use this, you should be aware what you are doing, also what kind of effect it has on the testing. And even if you have well-known databases like the CFAR10 benchmark data set, this is really a standard for image processing, you figure out that there are already transformed images in there. It's obviously the same picture of a car, it's only slightly transformed, and you have to be very careful what to do and how to interpret the results from these transformed images. This is my message for you. Use data augmentation, but when it comes to testing, be careful how to interpret the results. Thirdly, keep data independent. So usually what is done, the data is split into training data and testing data. And of course, the testing data has to be statistically relevant and not, let's say, should be representative for the data set as a whole. So this is usually done to split up the data. However, on top of that, if you see this improvement cycle of AI development, you set up an AI learning algorithm, you train it, you test it, you analyze the results, you define the improvements. If you do this for a long time, for hundreds of times, you figure out that somehow the lot of analysis on it will somehow go into your training. So the training and testing is not independent. So the recommendation here is really that test data can somehow become part of the training, and that you update the test data to get meaningful results, especially if you're working on this for a long time. Fourth principle, testing after changes. In software development, of course, everybody knows regression testing, meaning you have an understanding if you make a change of what part of the software you have to test. The intention is not to do a full test of the whole software every time you do a small improvement. However, when it comes to AI software, we have to figure out in a connected system like that, where you have many interconnections, and the basic design idea behind it is parallel distributed processing. I was working with this Professor James McClelland at that time. It's the design idea is to have something in parallel, not sequential, to be massively parallel. And by this design principle, there is not something like a partial software testing of that. You need to test the full data set of the software here, and you need to be prepared to do it frequently and in full amount. So you need to consider this in your resource planning. So this is my message here. So the background is that you do this circle that I explained before many times. You have to run the software test through it many times, and you have to have the resources for it, because you are likely, and this is the practice for this AI development, have to do these circles many times. So let me summarize. Make BEV and HEV drivetrains benefit from AI. I presented 4 principles. Do continuous improvement of the database where it matters most. Use data augmentation with the consideration it may have on the test. Keep test data independent throughout the whole development phase, and do software test of the AI module frequently and with full data, and not just test the patterns of features that you have changed. If you do that, and if you apply AI to drivetrain optimization, I'm really optimistic that BEV and HEV drivetrains, which do not have the benefits of decades of experience by now, can very well benefit from AI. Let us use AI to optimize them, because if we don't do it, somebody else will do it. Thank you for your attention.